So very warm welcome once again to my YouTube channel Simulation Engineer. As you can see flashed on the screen, it's about XFLR5 Part 5. If you have never seen the other parts, the 4 parts which I have done already before, I will also put a link of the playlist of XFLR5 series where I have done complete validation, and I have even shown the step-by-step guide how to perform aerodynamic analysis for a 2D airfoil, and then go on to perform for a 3D wing analysis. And also I have done one tutorial on how you can simulate with some limitations the high lift devices, how you can do the transition prediction and compare it with the results. So I would encourage you guys to go there and have a look on the other parts which I have done for this XFLR5 series. So this part 5 will be today specifically about it's an old one, a very famous PA-28. So it's a Cherokee wing, so it's for this aircraft. You're seeing this picture on the screen. So I will be doing the wing analysis, so it will be kind of a direct comparison between 3 different wing plan forms, and we will see how it really affects the induced drag coefficient. So a brief history about the Piper PA-28 Cherokee aircraft history. It's like it's a very famous aircraft. It belongs to the family of light aircrafts, which has been built by Piper Aircraft, and it's been designed for flight training purposes and even for personal use, etc. The PA-28 family of aircraft, it is completely metalled, unpressurized. It's a single engine, piston powered airplane with low mounted wings and tricycle landing gear. So as mentioned earlier, these are the 3 wing planforms which we will be studying today. So the first one is the PA-28-180 series, and for each aircraft you will be seeing 3 views. So it's the plan view, you have a front view and the side view. In the plan view you can see this is a wing. So this is a constant chord wing, so that is there is no change from root to tip. And then there is a second one which is extended, so it's the same wing but with certain some more extension. So this wing planform has a slightly larger wingspan. And the third one is the tapered one. It is the series name of 181. So this wing is tapered in a sense that you will go till maybe mid of the span, and then after that towards the tip there is a smaller chord length. So we will be performing these analysis over these 3 wing planforms. So just to give you some more insight, these are the wing parameters. As mentioned earlier, the 180 series has 2 variants. So it's a simple or standard one, which is a constant chord, and then there's the extended one with an increase in the span of the wing. So, and in this for each aircraft I have mentioned also the important parameters. So I'll be using the washout, which is -2 degree at the tips. So you can achieve this by using twist parameter in XFLR5, and a root chord. So as it is constant chord, so the root chord and the tip chord, it will be of same length. This is the wingspan. The dimensions are provided also in inches and in meters, and all the wings have will be having a dihedral of 6 degrees. Yeah, if someone who has no idea what is dihedral, so this is the shape. So I mean it's like a V shape, so it's not really straight. So if you really see in each picture, this is the second view, the front view. If you see from the front, you can see that this specific angle. So it makes as is moved towards the outwards, that there is a specific angle here. If we draw a horizontal line here, so this will be the dihedral. Okay, so the last one is the tapered one. It has the same parameters, but obviously because of the tapered geometry, the tip has a different root chord, so it is also mentioned here. And it has a local span of 2.59. so if you start from there till this point, so it's about 102 inches, and further the rest or the remaining part will be the tapered part. So the flight condition which we will be using to simulate this will be mentioned or you can see here in the table. So we'll be using a speed of about 65.83 meters per second. It's about a Mach number of about 0.2. And the airfoil which is used here is NACA 652415. I will also put the link in the comments or the description section, so you can also get it or download the airfoil, but normally there are a lot of resources available where you can get the airfoil database nowadays. And at which height and sea level conditions also, so there is econometric viscosity, altitude is also mentioned. So we'll be using these conditions to flight conditions to simulate our wing analysis or perform our wing analysis. So I would say let's start with this Cherokee wing analysis, and we will now open XFLR5. So a very brief description. Normally the standard way of performing wing analysis in XFLR5 is to that you will first of all load your airfoil, and you then go on to perform the complete flight envelope analysis based on your Reynolds number. So one has to make sure that you cover all the polars of your Reynolds number, because in case of a constant chord or in tapered chord, you will be having locally along the spine of the wing different Reynolds number. So one should make sure that you are completely doing the complete flight of envelope to get proper converged solution once you are doing a 3D wing analysis. Okay, so and we will see how I have defined the wing design parameters and the airfoil which we have used or which we will be using here. So just once again, just for the reminder to show you that we will be using these three planforms I've already mentioned here, but this is just for the clarity. You can see much clearer now. So this is the chord, root, and the tip chord in case of a constant chord. Similarly, also in the extended version, the only difference here is that it has a smaller wingspan, it has a larger wingspan, and then you have a tapered geometry. So total wingspan is mentioned here, and then the root chord and also the tip chord is mentioned here in case of this tapered geometry. So this is how in XFLR5 it looks like. I've already mentioned the profile or the airfoil which I am using is a 652 NACA 415. So if you have an airfoil available, you can simply open from here and load it. It will be a DAT file. It's a database file. So once you have opened, make sure that the very important thing is that it has sufficient number of points available on your profile. So if I right click and select my NACA profile, I have to say refine globally or locally. So here this is the way you can actually redefine the number of panels, right? So make sure you have at least 100, or the experience shows that in between 100 and 150 is kind of a good compromise, and you get kind of a better converged solution. Sometimes in airfoil or profile shapes which are having very strong curvature, and you need to make sure that you have enough number of points later on for the analysis. Okay, once you're happy with this airfoil, you simply move on to the direct airfoil analysis. I will show you here because I am not showing completely all the steps which we'll be doing here, because it's just the repetition of the 4 parts which I have already done. So part 1, part 2, part 3 and part 4. You can consult part 1 and part 2 for detailed analysis of 2D airfoil and 3D wing analysis. So once you have an airfoil selected, in our case it will be just one airfoil, so you need to perform the complete flight envelope. So how you will achieve that? So for example, you go there and you say I wanted to do or perform a batch analysis from 1 million. So you simply type here 1 million and you go to about, let's say 5.9 million Reynolds number. You can add more increments, and even in some cases in your 3D wing analysis, it might be complaining that that at higher angles of attack it is not converged, or at some points at this span position the solution is not converging at this particular Reynolds number and this lift coefficient. So XFLR5 might complain that it's not been able to interpolate the results. So this means that you might have this some local Reynolds number missing. So you come back here, either you do again a batch analysis from this mentioned Reynolds number around that. So you add some smaller increments to get much finer flight envelope, and then go back, and hopefully the problem will be resolved. So there you can see I have done a complete batch series of all Reynolds number, and I have gone from about minus 5 degrees till 20 degrees. So once you're happy with this, you simply go to the wing and plane design. And I have already computed for this these parts, the simulation, but what I've already mentioned, I just wanted to show you now. So we can see that this is a dihedral, and we have also achieved our twist by specifying the required parameters. So what you normally do is you go there, first of all, plane. If you are starting from scratch, you say define a new plane and you give it the name of the plane. And if you are just simulating the wing, so you don't simulate elevator or fin, and body if you want, you can actually but it is actually not really recommended to take into account, because there are still some bugs, as it is mentioned also here. It's not still recommended. So if you have the plane inertia available, you can define that. Or in case of a wing, how you do that is we know our parameters. So you select your airfoil. It's just a one airfoil in our case, and you define the span wise, so it's the Y, and then you define the chords on offset. So further parameters can also be mentioned here, and you define that to get your desired wing shape. So we just close this one, and I will show you now the real 3 wings parameters which we have used. So for example, this is the first one, constant chord. So you just right click in your window here, and then click current plane option, go to edit wing. Once you go to edit wing, so we can see the shape, the desired shape which we have achieved for our airplane. So this is the total span, and also make sure that you just model half of the wing geometry, so not the complete, because we will be using symmetry boundary conditions. So it's just XFLR5 is just modeling the right side of your wing. So it's also less computationally expensive, and you will save a lot of computational effort. And it is recommended to use the number of panels, so span wise or in the streamwise direction, so chord wise, from 20 to 30 panels, which is kind of a good approximate compromise, I would say, based on the personal experience. So I'm not claiming this is the best number of panels, but you can stick with it and try with it. If you get some more better strategy for this one, just let me know also. So we can see that based on our number of panels or number of elements which we have used, we end up getting number of VLM panels. It is showing here, so it's about 1,800, and number of 3D panels which is about 3,600. So this is the aspect ratio we are getting based on our desired parameters, and we have a taper ratio. It's 1 because since it is a constant chord. So I think that's about it. Once you are happy with it, you go there, and the last step which you need to also mention is that since we have mentioned in our flight configuration data that we need to mention the weight. So I have used the wing mass for all the aircrafts like this one. So you get in there, you will get wing loading, and I think that's about it. Once you are happy with it, then you go on and perform your analysis. So this is the first one. Constant chord. So you have an extended version, so the same series but with an extended wingspan. We can see that here. So once again, you right click and you go there, and you can see, so there is no difference except the change in the wingspan. The rest is completely the same. So we have mentioned about dihedral of 6 degrees in order to get a twist of -2 degrees. So it is like all this upwash and downwash parameters. So in order to compensate for this, you normally add a twist in at the wingtip, for example. And then another important thing, I would recommend using X distribution chordwise and Y in the spanwise distribution, a cosine function, which will give you really you can see it's kind of near to the root as you go away there. So you're getting very fine elements spacing, fine spacing. Similarly, if we move towards the tip, so we'll also get fine spacing, and similarly also in the chordwise direction around the wingtip. So airfoil, we are having fine number of points, and then as you move away and go towards the mid of an airfoil, you get a little bit coarser element distribution, and similarly as you move towards the trailing edge, so you're getting a fine number of fine spacing there. Okay, and then we will simply specify once again the same parameters. You go to the other options and then click inertia and define the wing mass here. Alright, we have not changed anything. We'll move on to the last one, which is the tapered one. So once again, repeat the same step. Go to the edit wing section, and there is one change compared to the other two wings that we are using now, 3 wing sections. So the number 1, it has been shown here with this red outline. If you go to the number 2, so this is this one here. And again, remember, we are just modeling only half of the wing, so using the symmetric boundary condition, and it's only the right side is being modeled. So we can see that at this point, so you go from here till here, this is a constant chord, and then from section 2 to section 3 we have a smaller tip chord length, which can be seen here. It is highlighted also here. And the other parameters like dihedral, twist are the same, and the same number of distribution. We can also see, as in other two wings, we are getting the same number of panels. So it's kind of a good comparison, direct comparison between the 3 wings once we are finished with our analysis. So this analysis approach will be valid for all 3 wings. So normally how you do the perform an analysis, you go to analysis and define an analysis button, either or you can use F6 shortkey. So we will be using fixed speed as mentioned, our flight configuration, so 65.80 meters per second. It's about Mach number of about 0.2, and then you move on to analysis. So you can perform different types of analysis like lifting line theory and 3D panels. So first of all, I did like lifting line theory. It's a simple linear distribution. So normally this part or this analysis method does not include the viscous part, so you cannot predict stall. 3D panel, it is kind of give you viscous behavior too with the coupled approach. So you perform the inviscid part and coupled with the viscous boundary layer. That's why you can see this option viscous. So if you disable it, you are not calculating the viscous part. Obviously, depending on your wing or the geometry, how big it is, it will take some more time, some efforts. And also, as we have already seen earlier, that's saying ignore body panels, so recommended. Like we're not including any fuselage or any masses, so we have not modeled anything. We're just considering the wing, and that's it. So first of all, I did the LLT analysis, and later on I also did the 3D panels. I will show you guys in a minute the results. But the important thing is that you also mention the plane mass even here, or the XFLR5 automatically mention or pick it from your specified parameters once we are doing our wing design. And then the reference dimensions, one should not change this, just stick to the default. And then you have an aero data. So based on our altitude and temperature, you can get this these values. So also you can say this is the altitude and that's the temperature, and then you will get all the desired values. And you can see also that in case of a tapered wing, this is the wing loading based on the wing mass, and the tip Reynolds number is about 3.8 million, and we have a root Reynolds number which is about 5.92 millions. So this is the parameter which I was mentioning. If you have not covered these Reynolds number, not only specifically this number, but at least in this case we can say from 3 million towards 6 million with a smaller increment, so to have a much finer flight of envelope, and this will really assist in performing or giving you a better converged solution once you are doing a 3D wing analysis. So I think that's about it. Once you are happy with these parameters, you simply go on and perform the complete polars for these 3 wing analysis, which I have done, and I will show you guys just in a minute. So by the way, the polars which I have used, the angle of attack is from -5 to 20 degrees, and I started with the smaller increments, and just another hint, if in case sometimes you get some convergence problem, I would recommend to start with maybe a positive angle. So start from 0 towards the positive angle, you go to 10 or 20, and then you come back and start with the negative angle of attack. Or you can also, instead of having incremental delta alpha of about half of a degree, you can go out to about 0.1 or 0.25. Once you are getting a converged solution, then you can slowly increase that. Okay, so I'll just show you the results, you guys, in a minute. So we can see I have done LLT and the 3D panel method analysis. We can see that, for example, if we see this alpha versus lift coefficient, I will show you the enlarged view of this polar. So the black one, the red one, and the green one are the lifting line theory. So it's based on the Prandtl's lifting line theory, and we can see all these 3. So the black one, the red one, and the green one, they are not able to predict any kind of a stall. So it's just increasing, but the important thing which you can also observe in this 3 configuration is that because there is a slight increase in terms of a lift coefficient at the same angle of attack, for example, of 20 degrees, and because there is a change in the wingspan, increase in the wingspan of the red one, which is extended one, and the green one is the tapered one. And we can see that in the complete polar, we are not only getting a higher lift, but there is a shift in the complete polar. So this tapered geometry, it will give you overall, even in the linear range, a higher lift coefficient at the similar angle of attack. And the other 3 colors, so the blue one, the pink one, and this whatever you call it, lila or violet color, these are the one with the panel method analysis. So it's kind of a viscous approach. We can see that it's not going further. So this means after this point, for example, it's about 16 degrees, the solution, it's not able to converge anymore, which is an indication, because since this is a coupled, so it's a viscous coupled with a viscous analysis, that the wing, or it's really stalling at that point. It has been observed in all the 3 analysis. So the blue one, so it's about, this is the area which maximum lift coefficient is achieved. Similarly with the extended one, you get a lift also in this area, you see, and it's about an angle of attack, it's around 9 degrees, it's approximately around in the region of 10 degrees. So after getting a lift of about 0.9, the extended wing is being stalled. So if you see this one, which is the one with the tapered geometry, it's not only getting this completely shift, but it has achieved some much higher lift coefficient. So now also to even confirm this behavior, one can also see that in terms of alpha, so if we see the angle of attack versus the induced drag, that was actually kind of the theme of this presentation or this tutorial, is to see what effect these wing analysis will be having on the induced drag coefficient. And we can see directly that at even for example at an angle of attack of, let's say, 15 degrees. If we go there, yeah, so this is 15 degrees. So the black one and the red one and the green one, these are the one which with the lifting line theory, there is increased induced drag, and with the increase of the wingspan, the induced drag coefficient decreases. And even with the tapered configuration, there is a considerable decrease compared to the one. So with this black color, with this standard configuration, there is a considerable decrease of induced drag, which also confirms the theory. So by adding even some tapered geometry, or if you add the sweep, you are trying to let's say reduce also the drag, and this means once you have a less induced drag, this results also in better lift coefficient, or increase in the lift coefficient. And this behavior can also be seen if we go there in for example, this is at an angle of attack approximately about 9.2 degrees, and we have a lifting line theory for the constant chord, and this is our induced drag. So it's this is the wing planform. So we can see that it goes from this. So if I change it to now an extended one, I can see that even visually that there is a decrease also in the induced drag coefficient, and similar behavior can be observed also, that overall there is a decrease in the induced drag coefficient, right? So and now I will show you one by one each polar to have some better picture how it really looks like and what kind of behavior is being really achieved. Okay, so we have already seen that, but just to get some complete picture, so this is in terms of induced drag, alpha versus induced drags. It's a similar plot. We can see that by increasing the wingspan and also getting a tapered geometry, induced drag coefficient is reduced considerably. Even at a higher angle of attack, this can be observed. And these are just the LLT results, so lifting line theory, and similar behavior can be observed in terms of alpha versus the lift coefficient. You are getting not only a higher lift at even a higher angle, but the complete, there is a shift in the complete polar with the tapered geometry. And we can see that if we have a direct comparison of the CL versus the induced drag, that the lift coefficient increases with the tapered and an extended wing plan form compared to the constant chord or a simple form of the wing, which results in a higher induced drag, but the tapered geometry or wing extension leads to lesser induced drag, which also complements that there will be a lesser lift coefficient. In terms of performance, so you normally judge the performance of your aircraft, of your wing, based on this glider ratio, which is the CL over CD. So we can see that even it is also performing better with the tapered one compared to the standard one. Also the similar case can be observed even with this extended one compared to the constant chord plot. And as we have seen earlier, just for each wing, so I have just here made a plot to have a direct comparison between the three wings, and we are seeing here the local lift coefficient versus the span. So it's just all these three wings we can see, and we can see here quite clearly that at an angle of attack of 15 degrees, the one with the tapered geometry you are getting, so this, if you just see this area under this curve, there is a considerable amount of increase in the lift coefficient, which is achieved as a result of reduction in the drag coefficient. So this also confirms the theory, because once you are getting because the lift induced coefficient, drag coefficient is being produced because of these tip vortices and this complete complex phenomena which is occurring here over there. So this also reduces the strength of these vertices, and also in turn reduces the induced drag. So if you have a tapered wing geometry, we can see that there is also a increase in the lift coefficient with an extended wing geometry, but not so considerable effect. But one can also see that it's still really prominent, that if the shape or the wing planform really plays an important role based on your desired objectives for your particular wings or airplane analysis. And once again, if we see again the direct comparison between the three wings, we can see here very nicely the wing plan form for each of the wing, and the important parameters being marked with the red line. So it's the constant chord, and we have an angle of 15 degrees. We can see that we have an CL of about 1.18. The same parameter, just extended wing, we have a CL of about 1.2, and also there is a reduction in the drag 0.096, 0.093. And if we go to the tapered one, there is considerable amount of increase in lift, and there is overall drag reduction compared to the other two wings. Okay, so if we now wanted to see some pressure distribution plots, we can also add some streamlines inside. So remember, you can also just see the CP distribution, the pressure coefficient distribution, which is only possible with the panel methods, because since we are also coupling with the viscous analysis, and we can see this quite well. Yeah, so this is a nice view just to see how it really, because I'm just using a 9.2 degree angle, so it is in case of, I think for the one with this constant chord with a simple configuration is about 9.2 degrees, and then after that it's not even solving further because it is being stalled, this configuration. So if we move to the extended wing, we can again see that there is you can see, even observe a change in your tip vortices. Similar can be observed also here. Another important thing you can also observe here is the lift distribution. You can directly plot that. So if we really see completely from this front view, one can even add the transition also on distribution. So you can even add a downwash, so how it really affects the downwash, the different wing plan form or the shapes. So we can even go and just plot for the constant chord, and once again if we plot it for the extended one, this is again the downwash, and also the streamlines are showing very nice vortices, these tip vortices, which can be observed here. And if we go again to the tapered part, so you can also see that there is a decrease in the downwash. We can also see with the downwash distribution. You can also let XFLR plot induced drag, viscous drag, moments. You can also add even the surface velocity distributions. If you want, you can animate each angle of attack, so it will be showing you the angle of attack and the desired results at each at the specified value. So XFLR will keep on simply plotting at each angle of attack. So you see here, you can see the change in your airfoil distribution, and you see the angle of attack is changing. So I think that's really about it as far as this three different wing analysis or the comparison is being concerned. And we have already seen quite nicely that the effect of the wing plan form and the usage of the Prandtl's lifting line theory compared to the panel methods. So panel methods give you much realistic results because it is being calculated coupled with the viscous part of the analysis, wing analysis, and then you can compare them even with somehow even with the real data if it's available. But in the end, I would encourage you guys to go and have a look at my XFLR5 series, because this was the part 5, and I have done prior to that 4 parts, and hopefully all these videos will help you guys in your studies or in your maybe any projects you are doing. And if you find these videos useful, just give me a thumbs up, and don't forget to subscribe to my channel and share my channel amongst your colleagues, friends, or family. And in the end, I would just conclude this with this remark that XFLR5 is really a very good preliminary tool if you are doing any airplane sizing or you're designing a wing. Obviously, there are further so many steps which are has to be done, but just to get some preliminary ideas, design ideas at low speeds, it's really a very good tool. So with this, I wish you a very nice day. Take care, and thanks for watching this video. Bye bye.